even in the case k equals 3, it's possible to have intersections that don't generate something. If I have ij and kj versus ij and jk. So that's what's happening here. These intersections are the kind that don't generate anything. Now I'm going to vary my phase. So as I vary the phase, so first of all, something new happens here. These things are now generating new walls. That's a kind of mild thing, which actually we don't consider as a kind of topology change. I'll try to spell out the rules as we go on. But you can see that that's somehow not a discontinuous change. Nothing sharp is happening. Now, as we come close to this critical value of the phase, now something quite sharp is going to happen. So here we have, 3 sort of secondary walls being born and heading out to infinity. And heading out to infinity in a quite particular way. Now then, there's this critical moment. There's this critical moment where there appears a kind of network. 3 walls hitting each other at a common point. And then on the other side of that, now these secondary walls are coming out in a quite different way. So let me show you again. So you see they're going out that way, and then suddenly they're going out the other way. So that's a kind of discontinuous change which you could detect. For example, if you looked at a little path that goes from here to here, let me hold my finger there. So a little path that goes from here to here, it's crossing 2 walls. Okay. It's crossing 2 walls here, but when I change to the other side of the thing, now it's crossing only 1 wall. And so that would make a big difference. So my path lifting rule has really jumped at this moment. That's different from those other changes which were more mild and actually didn't change the path lifting rule. So there's a jump. There's a jump of the path lifting rule which is associated to the appearance of this object. So this is the new object that we want to count. That we didn't have any analog for the quadratic differentials. So now let me try to define exactly what the objects are. So the new possibility is to have an object. So let's say before one way of describing the saddle connection is that it's actually 2 S walls that are hitting each other head to head. So I had an IJ wall coming out that way, and JI wall coming out that way that hit each other. Now here, and in general, whenever I have S walls that hit each other head to head, that's this new object that I want to count. So here, suppose I have an IJ branch point, a JK branch point, and an IK branch point, and they give birth to 3 trajectories. An IJ trajectory, here's a JK trajectory. Now, according to my rules, those 2 would have given birth to an IK trajectory going that way. So those would have given birth to an IK trajectory going that way. But now, here what's happening is that I have an IK trajectory coming the other way, coming out of this branch point. So it's a KI trajectory that way. And so similarly, in fact, here this KI and this IJ are giving birth to a KJ, and here these 2 are giving birth to a JI. So I have this whole locus where the S walls are colliding with each other head to head. And it makes a kind of a finite network of these trajectories. And it's these finite networks that will give us the Valence and Thomas invariants.
The trees, yeah, okay.
Well, they don't have to be trees. So you can have more complicated things. I mean, you can have something like this. In fact, there's a lot of topologies now possible. There's all kinds of. It's not at all like the case of quadratic differentials. But let me now make a definition. And then maybe I'll stop. Well, actually, maybe I'll make the definition at the beginning of the next. So let's just say that our new Donaldson-Thomas invariants will be counting such finite networks. And this one again, this one is rigid, so it will contribute. This will contribute omega equals 1 like before, and there will be some more elaborate rules for the counting of things without these topologies. Okay, so I think I'll stop.
Just one remark. Such networks are a very old thing. Fukaya and all they developed Morse category. You consider functions on a manifold. And for any two functions, you get a gradient of difference, and we draw exactly this trees.
Oh, great! So
yeah, so it's
fantastic.
So already for degree 3, we will have arbitrary number of ends for those trees.
Even for degree 3, even for k equals 3, it can become arbitrarily complicated.
So, is there any reason that I had to have all of phi2 to k non-zero? I mean, if I took a generic phi3 such that the spectral curve was still simply ramified, wouldn't that be an easier case to think about first, or is that?
It turns out that the easiest case, okay, maybe that's also easy. There's one case that's very interesting that I'll say a little bit about next time, which is the case where essentially only phi2 is non-zero. So you have phi2, and you turn on all the rest of them only a tiny bit. So the picture will look like, yeah, let me show you a picture of that. Where's the one? Oh, well, in fact, so the picture is like this. So remember, in the k equals 2 theory, we had just these simple sort of S-wall networks, 3 things coming out of each branch point. Now, suppose that I take phi2 to be quite big, and I turn on phi3 just a little bit. Well, the effect of that is to take each branch point that I had for phi2 and kind of resolve it into 3 branch points. Well, suppose k equals 3. Then it resolves it into just 3 branch points. So here I've got a little triangle of 3 branch points. And so what you get, the network now becomes a kind of thickened version of the network that you had before for k equals 2. So the picture for k equals 2 was like this, right? As you varied it, there was a moment when they hit each other. There was just one thing that happened at that moment. So now you can do the same thing, but with these higher rank ones. So now, it's the same thing. These cables kind of wind around, right? They have a little bit of internal structure. So like at this moment, there's about to be one of those finite networks that appears here. So that there's a little bit of internal structure, but then there's also a bunch of non-zero invariants that occur when the 2 cables hit each other. Right, at this moment, oh, sorry. I don't have exactly the moment where I see, I do, but I have to go all the way around. Exactly at this moment where the 2 cables hit each other, there's a bunch of non-zero invariants appearing more or less at the same time, right? In the limit where I went back to phi3 equals 0, they would be occurring exactly at the same time. So this is the thing that kind of reproduces, so Fakin-Goncharov had a thing for, had this abelianization also for higher rank systems. And it again used the data of a triangulation. And the way I understand it, so for us a triangulation doesn't seem like so natural. It's this whole network that's natural. But in this limit, it again kind of looks like a triangulation, right? And so here, this gives you some finite collection of topology changes, which is like a finite sequence of sort of elementary transformations. There'll be a finite sequence of those k gammas. And exactly such finite sequences appeared in Fakin-Goncharov's thing. They said when you flip the triangulation, you have to make a whole bunch of moves. Those moves correspond one-to-one to these little cables hitting each other. So that's the so that's the interesting limit that we know about.
Can you see some kind of Lagrangian manifolds in this dimensional Cavalier form?
Yeah, so that's very confusing actually. So it's not. Oh, sorry. No, I have in mind a different picture. I don't know how to think about. I mean,
it's not even. Is it even obvious what the three-dimensional
yes, it's always here. You put kind of AD spaces instead of C2. Instead of quadratic. But there are a bunch of constructions.
Super AK chain.
C square divided by pi group.
there should be some kind of relation, well, which is coming from cell relations of well, if you can see on these pictures.
Sorry, a relation between what?
Well, you say that there's just path like that equals to path like that. But
Oh,
they are well in the group there are
the homotopy invariance
of the homotopy invariance, which is just equivalent to cell relations of the group. Goes for.
Let's see.
There are 6 terms in a sense. The cell relations for.
Let's see. We might have to discuss. I don't know immediately. There is something that occurs here where you're trying to get the formula for the vial, the longest vial word, longest element of the vial group is a product of transposition. That does sort of occur here. But yeah, that's the only thing I know.
Okay.
Thanks.
Yeah, thanks.